Welcome back to software engineering class. So this time we'll be looking into the fundamental concepts of testing. But first, if we want to recall what is testing, it can be compactly defined by these 3 points. The first one is what is the objective of testing, none other than to uncover errors, and how to do it with the criteria that we want to do it in a very complete manner. We want to look at every angle, to do every diagnosis and so on. But note that everyone has a constraint, and that is to use the minimum effort as well as time in testing. Testing consists of a set of activities which can be planned in advance and conduct systematically. Okay, and normally the testing begins at the component level, and it will works outward toward the integration of the entire computer-based system. So for that matter, we will first look into component testing. This is the big picture of the testing strategy. So we start with the unit testing. Okay, and then we move outward into integration testing, validation testing, as well as system testing. And these are all connected to the different procedures, okay, in developing any software, the coding part, design, requirements, as well as the system engineering itself. So the unit testing is normally considered as an adjunct to a coding step. Okay, unit testing makes a heavy use of testing techniques that exercise specific paths in a component's control structure to ensure none other the complete coverage and the maximum error detection. What are the errors to look out for apart from the obvious error? The first one is what we call the unintelligible error description. Second, there are the errors that were encountered in the procedure, but it does not, or they does not correspond to the error that were noted, and this needs to be documented very well. Okay. And then third, the error condition that causes a system intervention prior to error handling itself. Number 4, exception condition processing, which is incorrect. And finally, the error description that does not provide enough information to assist in the diagnosis to find the cause of any error. To uncover these errors, we must first go back to the concept of use cases, where it started from the requirement step. We gather user stories and then we refine them to use cases as well as analysis model. So what we need to do is, based on these use cases, we need to create specific test cases. And these test cases must cover both the functional as well as the non-functional requirement. Okay, so functional requirement is exactly what we ask the system to do, but the non-functional requirements are the behavior behind this function. For example, if you want to send an email, sending an email is a function, but then you want the email to receive the next person within a certain latency and so on. So that latency is the non-functional requirements for this function. Okay. However, executing test cases to demonstrate that the component is running correctly is most often not good enough. So what we need to do actually is to write also the anti-requirements or the negative test cases. So when we do the testing, we run the normal test cases as well as this anti-requirement. So we are sure that all the cases, the possible cases, can be covered. Okay, so no surprise error when our product receives the users. Now that we have our test case, let us understand a little bit this schema that illustrates the unit testing. So these test cases is linked to a module or a component. This is the actor behind the testing, the software engineer, and obviously we want to produce results from this process. So the test case involves 5 steps. Okay, these are the 5 of them. Okay, the first one is the testing of the module interface, because we want to ensure that information are properly flowing in and out of our program, which is under test. Okay, and then for local data structure, we test it, we examine it to ensure that data which are stored temporarily, it maintains its integrity during all steps in the or in any algorithm execution. Okay, and then we also have what we call the boundary testing, because it is a general knowledge that software, it often fails at its boundaries. And for this matter, we will look into it furthermore later in details, okay? But then we also need to do the independent path testing, okay, because our algorithm have a control structure, okay, and we need to make sure that all the statement in the module, okay, all the path in the module, it has been executed at least once. And finally, we also need to test the error handling path. So these are the paths that we create, okay, we create in cases where we find error. Okay, so this must be created, and then we need to test this error handling path as well. One thing to note, the term test cases, this concept is used interchangeably with the term test script. So here I just want to highlight one of the definition that I prefer. That is, a test case is actually the step-by-step procedure that is used to test an application, while the test script is actually the set of instructions to test any application automatically. So the term test case, it is used in the manual testing environment, it is done manually, and it is developed in form of templates. But the term test script, it is used in automation testing environment, okay? So this is done by scripting format, it is developed in the form of scripting, and then we can automatically run it, okay, to test for our error, alright? Okay. And when we do the unit testing, we want it to be cost effective, and we want to avoid at any cost an exhaustive testing. Okay, just imagine in this whole procedure, we need to consider the combination of input as well as the test cases. Okay, and if imagine a move generator for a chess scheme, how many combination of input and test cases does this case have? And another example here, if we consider a 100-line program in the language C, so after some basic data declaration, the program contains 2 nested loops, okay, that execute from 1 to 20 times each. It depends on the condition specified at the input. But inside the interior loop, there are 4 if then else construct. Okay, so in this case, there are approximately 10 to the power of 14 possible paths that may be executed in this program. So to put this number in perspective, let's say that we are using a magic test processor, okay? So if this processor works for 24 hours a day, 365 days a year, this magic processor would work for 3,170 years to test the whole program. So this would undeniably cause havoc in most development schedule, and therefore it is reasonable to assert that exhaustive testing is impossible. And for that matter, we need to be selective. In cases of large software program, we tend to select test cases that are crucial to the success of the project, or the one which are most error prone. In the component testing, without going for the exhaustive approach, that's what we call the white box strategy. Okay, other names are glass box testing or structural testing. But using white box testing, we can derive test cases that guarantee all independent paths. Okay, all independent paths within a module have been exercised at least once. Okay, it also exercise all the logical decision on their true and false sides, execute all loops at their boundaries and within their operational bound, and exercise the internal data structure to ensure their validity. To ensure that all the independent paths have been executed at least once, we first need to understand what is independent path. So here, for example, on our left, we have the flowchart, okay, a control structure flowchart, which can be translated into a flow graph. So here in the flowchart, we have the start and the end. Okay, in between we have the condition set and the function set. Okay, and this in the flow graph, for example, here we have the 1. Okay, so this one, node 1, referring to condition number 1. And then we have the function 2 and the condition 3 together in one node. Okay, and so on. So for example, here we have 4 and 5 together. We have 6 separately because this is further separated into 8 and 7, and so on. Okay, so what are independent paths? The example is this route, okay, where we have 1 and going to 11. We also have path 2, for example, on this route, 1, 2, 3, and then move to 4, 5, 10, going back to 1, and then reaching 11. Or path 3 where we move here to 3 to 6, 8, 9, 10, 1 and 11, or 6, 7, 9, 10, 1 and 11. What is not an independent path is, for example, path A, which constitute of path 2, okay, 1, 2, 3, 4, 5, 10 and 1, but it goes back into 2, 3, okay, and then it takes the other path 6, 8, 10, 1 and finally going to 11. So this is not an independent path because it's actually a combination of path 2 and path 3. And there are no specified 5 with new edges that has been introduced. So we don't need to look into this path. We only need to focus on independent path when we want to do the testing. There are different types of white box testing, okay, available now, but here I'm just listing 3 of the most basic ones. Obviously, if you are interested, you can look more, okay. So the first one is basis path strategy, and in this strategy, we use the cyclomatic complexity, or the notation is BG, to decide on the number of paths that we need to ensure the coverage, okay, and it has a foundation in graph theory, okay. So the graph that I showed you just now on the right, and this matrix actually provide us with an extremely useful idea of how complex a code is. And this is computed in one of the 3 ways. The first one is to look at the number of regions of the flow graph to understand how many, what is the VG. Okay, so for example here we have one region 1 to 11. Okay, we have the second region. The second region is from 1, 2, 3, 4, 5, and then you go to 10. The third one, this one, and the fourth region is this one. So here in this case, we have 4 regions, so the VG is equal to 4. But obviously, we can understand from this example that looking for region can be quite tricky. Okay, this is a simple case, but what if we have more complex cases? And how do we know that we don't miss any of the region? Okay, so for that matter, it's preferable to use the formula from number 2 and number 3. So how do we compute number 2? It's actually to have E, the number of flow graph edges, minus the number of flow graph nodes plus 2. So we have the edges here. If we look edges, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, so we have 11 edges with 9 nodes, 1, 2, 3, 4, 5, 6, 7, 8, 9, minus 9 plus 2. And we will get the same VG, which is 4. Okay, so this is a better way of computing the cyclomatic complexity, okay, because it is more obvious. But again, to find the edges can also be quite tricky. Another way to look at the complexity is simply to look at the number of predicate nodes. So what are the predicate nodes? These are the conditional nodes in our control structure. So for example, in our example before, we have 3 conditional node, and simply add by 1, so we got 4 as well. Okay, so this is the basis path strategy, and then we also look at what we call the condition and data flow testing. So in this strategy, the testing will focus on the program logic, okay, on the data flow and so on, the condition and so on. And finally, the loop testing, okay, we know that our loops can either be simple or nested. So we consider the loops and the degrees of complexity for each loop. Talking about cyclomatic complexity, there are a number of studies that indicated that the higher our VG, then the higher the probability of errors. So our focus will be on simplifying our codes and programs, okay, in each component, so that we can have the lesser probability of having errors. In case of loop testing, if we have simple loop, so we can use the following set of tests, where, for example, n is the maximum number of allowable passes through the loop. Okay, So first one, we need to test the code when we skip the loop entirely, what will happen. And then try to see if only one pass through the loop, two passes through the loop, n passes through the loop, or n minus 1 and n plus 1 passes through the loop. Okay, so this one is actually number 5 is the boundary condition. Okay, but this is how you do with the simple loop. And then if you have a nested loop, okay, nested loop, we start at the innermost loop, okay, and then we set all outer loops to their minimum iteration parameter values. For example, start with 1 and so on. Okay, so we test the minimum plus 1, the typical values, max minus 1, and max for the innermost loop first. Okay, while we hold the outer loops at their minimum values. Okay, and then we move out one loop and set it up as in step 2. We hold the other loop at their typical value, and we continue this step until the outermost loop has been tested. Okay, so in nested loop, you go one by one, okay, from inward to outward. And then we also have the concatenated loop. Okay, so this is the loop of a concatenated loops. So in this case, we'll try to loop, okay, if the loops are independent of one another, then we treat them as simple loop. Okay, so this one is a simple loop by itself, and another one is a simple loop. Else they can be considered as a nested loop. So we go back to the two basic loop strategies just now. Okay, for example, the final loop counter value of loop 1 is used to initialize the loop 2, and so on. If white box testing focus on the control structure behavior, there's the complement strategy, which is called the black box testing. Okay, this is also called the behavioral testing and functional testing. And try to validate the requirement without looking into the internal of programs. Okay, so the attempt to find errors are in the following categories: to look at the incorrect or missing function, at the interface, okay, the errors in the interface, errors in the data structures or external database access, behavior or performance error, or the initialization and termination of error. Okay, so this is used at the boundaries for unit testing, but it also tends to be applied during later stages of testing, for example, in the integration testing. In component testing step, the black box testing especially works in the boundaries. So for that matter, we look into the boundary value analysis. But first, we need to understand what is equivalence partitioning. So equivalent partitioning is actually partitioning the expected data that we are going to work with. Okay, for any specific variables and so on, we need to work with data. And for this data, and based on our particular use case, we try to partition our data. So for example, here, we have a valid partition between 0 to 100. Okay, so the invalid partition are the one from -1 until -infinity and 100 to infinity. But if we understand our use cases properly, we might be able to further partition our valid partitioning into smaller partition. Okay, because we know for each partition we need to do a specific test. Okay, and then based on this, we are going to do the combination test. So for example, here, let's say this number are age. We can maybe say that 0 to 64 is the normal age, and then 65 to 69 is the age where we can get diabetes easily, for example, and so on. So we partition the numbers further, okay, and from there we do the testing. And based on this further partitioning, okay, we will do the boundary value analysis. So on these values, for example, on 0, on -1, on +1, okay, we need to put these values into our test and to see whether our function work properly or not. Okay, because we tend to have errors at these values. And for each partition, we will do it.